Okay, yeah, welcome back. Let me just double check. Yeah, okay, looks like it. Okay, well, yeah, welcome back to strong field laser physics. On this time we'll talk about recollision. Yeah, so this is hang on, I need to switch one more time. There, yeah, okay. This is a very powerful idea. As I mentioned, it links strong field physics to collision physics, and namely, to say it in a few words, the electron that's first emitted by the laser pulse, yeah, and then drifts away, can also return to the ionic core. Yes, so it first drifts away, it gains energy in the continuum, and then it comes back and recollides. And this recollision takes has very drastic consequences. There's one important paper that's always cited over and over again by Paul Corkum. I think it's now cited more than 8,000 times. That introduced this idea back in 1993. There were a few papers that suggested similar things, but the one paper that's always acknowledged for that is the paper by Paul Corkum. And it's really a remarkably simple and powerful idea at the same time. Let's take a quick look at our model of strong field ionization so far. Yeah, so you can tell that comparing this to the picture on the previous slide that I'm now skipping something. Yeah, so here our electron tunnels and is then accelerated in the laser field. And so far we just said, okay, it has this canonical momentum, and this for using this we can actually find the momentum at the end of the laser pulse, which is what we would measure in an experiment. Back at the time in 1993, besides these direct electrons that we discussed so far, there were these three effects that we introduced in the beginning known, namely the high energy plateau in the photoelectron spectrum, or actually, or at least high energy electrons. The plateau was actually discovered a bit later. Then there was high harmonic generation, which is actually the most prominent one of them. And there was non-sequential double ionization. And these effects were still all unexplained. And these actually gave rise to much thinking and much work that was done, and finally collimated in these papers. Okay, so the idea was we look at this, and now we take a close look at the trajectories. Yeah, so for example, we have this one here. Here, our electron trajectory is initialized at this particular phase. So in other words, the electron tunnels at this particular phase and is then accelerated by the laser field. In this case here, moves like this. And then we can also go to another phase, for example, this one. And here, the electron moves away like that. And now let's go take another step. And here, yeah, this time it goes in a different direction. And it actually first travels to the opposite side at which it travels at the end of the laser pulse, or later in the laser pulse. And so it actually crosses the 0 point here again. And here it didn't do that, but here it also did that. Yeah? And then if we take another step here, it doesn't do that. Yeah, so there are the observation here, and you made this observation yourself, but maybe you didn't recognize it when you solved the first homework set. Yeah, there you found different trajectories, and if you've taken a close look at them, you would have seen that some of them return to the core, others don't. Yeah, this is our interesting observation, and we'll write that down. So first I need to start the new chapter. So this is now chapter 5. Recollision and rescattering. And then we have 5.1 types of trajectories. Okay, yeah, so we can write down the equations of motion, but I would skip them here in the interest of time. I mean, we've written them down before several times, and so I just write observation using the classical model on some trajectories. The electron can return to the core within one optical cycle after, well, tunneling. That's such an important observation. It gets a box. Okay, now our question is when, what trajectories, which trajectories are those that return to the core? Yeah, return time. Yeah, so which trajectories return and how does T1, the return time, depend on T0? Yeah, so who has an idea how to find this? If you think of our semi-classical model, yes, and you think of the trajectories, yeah, so a straightforward way that I would use is simply, yeah, so here we initialize our trajectory. Is that a pointer? Come on. It's not working, is it? Okay, so we initialize, we initialize our trajectory, and then we just propagate it until it comes back to the core.
And we see the point where it goes back.
Yes. Yeah, so let's initialize trajectory, propagate numerically until x of t switches the sign, right? Yeah, this is precisely what how we can do this. And yeah, the result looks like this. Do I have this here? No, I don't. Too bad. Okay, So the result looks like this. So I try to sketch it. We have here the initial time. Then we have here the electric field. Sorry, what's the question? Oh, yeah. Yes, so we have here, this is the electric field, E of t. This would be 0. This would be E naught minus E naught. And then we plot on this side the travel time. So the time it takes for the electron to come back, T1 minus T naught in units of an optical cycle. And the result is, actually here is 0. Say this is one optical cycle, and the result is this. And then here we get the same here. This would be 0. So it starts at 1, not at. And then again here. And the shape is not quite correct that I drew here. The shape is a bit more like this. Yeah, and the result, to put it in words, is that half of the trajectories return, and if you divide up your laser cycle into quadrants, so this would be the first quadrant, this would be the second quadrant, the third quadrant, and the fourth quadrant, then trajectories born in the first and the third quadrant they return. Electrons born in the quadrants 1 and 3 return. So this, whenever the electric field is decreasing, then the electron can return. And this actually makes a lot of sense, because then this restoring force here, so this part of the field will drive the electron in one direction, and that part of the field will drive it in the other direction. And when the field is falling, then this restoring force actually has a chance to drive the electron back to the core. So let's assume the electron is emitted up here, so close to this maximum. Then all of this part will be used up to slow down the electron to 0. And then this part drives the electron back to the core. And if the electron is emitted to in that part here, then actually this field is not, that field here is not enough to compensate that acceleration. Okay, there's a very nice method to find the recollision time, and I say it one time, and then we'll derive it, and then we'll interpret it. And the method is that we apply a tangential to the field at the time of tunneling, for example here. And then when it intersects the field again, this is the return time. And this gives us the result that when we do it up here, so if we do it up here, the tangential is horizontal. So it will actually return after one cycle. So here is one cycle. If it's in this point, then it will immediately return. If it's after this point, then it will never return. So it's a very simple way. It's very useful if you make some considerations. And now we will derive it.
So in the second part, there's no chance that the electron will return, right?
Exactly. Okay. Okay, so use canonical momentum to derive a graphical way to find T1. Okay, so first we write down the canonical momentum. mv of t plus ea of t. Yeah, and this we set equal to the canonical momentum at the time of tunneling. Yeah, so this would be p of 0 plus ea. P of t0. Yeah, and this is of course this we set 0. And then we rearrange for the velocity. Yeah, so v of t equals e over m times a of t naught minus a of t. Yeah, so this is very simple. Yeah, the velocity at any time during the laser pulse is given by the current vector potential minus the initial vector potential, actually with a negative sign. Okay, now we integrate to obtain the location of the electron. Integrate x of t equals from t0 to t. So we neglect here any initial position, which of course gives a certain correction if you include it. E over m, and then we plug in this result here. A of t naught minus a of t. And then we integrate. Yeah, so the first term is a constant. A of t naught times t prime, t naught to t, in those limits. Then we have e over m, integral from t naught to t, a of t prime dt prime. Oh yeah, I forgot the dt prime over here. And we cannot use t because t is in the limit. Okay, then we have here e over m. I want to write this one first. T minus t naught times a of t naught minus e over m. Now the integral over the vector potential. So this is not the derivative of the vector potential, which would be the electric field. It's now the integral over the vector potential, dt prime. And this we give this one a new name, namely f. Now, quite obviously, if the So f of t is the integral over the vector potential. The electric field is the negative derivative of the vector potential. So quite obviously, in a CW field, this would be exactly the same. Yeah? So A of t naught equals f dot of t naught, while E of t naught equals minus a t naught, which equals then minus f double dot. Yeah, and so for long pulses, yeah, so for CW it's obviously the same, and for long pulses it's actually very similar. And I brought you an example for this, in case you don't believe me. And you shouldn't believe it just because I say it. Yeah, so this shows here on the left-hand side E and actually omega squared f, so it has the same, because when you take the derivative, you get this omega squared, since it's two derivatives. So this is shown on the left-hand side for a long pulse, and on the right-hand side for a short pulse. So you see that for a long pulse, it's really essentially the same. For a short pulse, there's slight differences. But I want to emphasize that this is really a short pulse, a very short pulse. Yes, please. Oh, now it works again. Yeah, this says E of t and omega squared f of t. Yeah, the amplitude of f and e is actually different, yes. Yeah, but it's different by a constant, and this constant is omega squared. Yeah, so I should correct what I just wrote on the iPad. Yeah, so this is actually not true. Yes, E of t equals omega squared f of t. Yeah, but it's just a constant. Yeah, so for our method with this tangential, it doesn't actually matter. Okay, but we're not done yet. So now rewrite the actually, which equation is this? This equation here. So this equation here is 5.5 in the script. As follows: x of t equals e over m. T minus t naught f dot of t naught. Yeah, so instead of a, we use f dot minus f of t plus f of t naught. And then, yeah, so what we want to do is we want to find the recollision time, which we call T1. For t equals T1, we have x of T1 equals 0. And this gives us the following result. Oh, yeah. F of T1 equals f of t naught plus T1 minus T naught f dot of T naught. So what did I do? I set this to 0. Well, then we can just multiply with the constants. We don't care about them. And then we have here This is just the offset. And f of t, what happened to that guy? Here, this is on that side, yes, this we dragged over to the other side, and then we have here, yeah, just this term, that's that term, yeah. So when this is set to 0, the constant eliminated, and that over there. Then we get this result. And now we'll do the graphical interpretation of this. No, this is actually still the same point. So, graphical interpretation. Well, I first draw f of t. Okay, I'm not happy with the position of the x-axis. So it's here. Yeah, and then we pick some point t0, maybe this one. Now, f dot of t0 times t1 minus t0. This describes, actually this whole thing here, this describes a straight line, yeah, offset by f of t0, which is this point here. And then t1 minus t0, yeah, that's some point here, some other point here, and this is a straight line. And the slope is the derivative of f of t0, so it's this here. Yeah, so this is f dot of t0 times t minus t0. And then this point here, this will be t1. And so you can see that here, here this gives us a relatively short travel time. T1 minus T0. And if we consider, for example, that point here, we get a much longer travel time. Let's call this T1 prime, T0 prime. So it's quite neat.
Shouldn't the slope at the point be straight line, like parallel, not?
Sorry, should it be what?
0.
The slope is 0? Yeah, it's not exactly. It's not exactly at the top. The top is there. No. At this particular point, it would then arrive somewhere there. Yeah, that's exactly correct. Okay. Is this clear? How this works? I think it's very intuitive. Okay, and now we can actually use this method will now actually also help us to calculate the energy of the returning electron. Yes, because we have already an expression for the velocity, yeah, which is this difference of this one here, yeah, this difference of the vector potentials. It's actually 5.4 in the script, which we will use now. So 5.3 is return energy. Yeah. Use equation 5.4. E1 equals m over 2 v of T1. Yeah, so this would be the energy of the returning electron, and now we just plug in equation 5.4. A of T naught minus A of T1 squared. Yeah, and that's the V squared, yes, thank you. And what is the, yeah, so the question, I mean, now we have an expression, and now it's of course interesting to calculate the maximum energy. Yeah. So what is the maximum energy, and when is it? I mean, quite obviously, we can set some limits. Namely, either of these can have a maximum of A naught. Yeah, so the maximum or the minimum that this would be 2 UP. Yeah, because for the maximum energy, of course, because we don't consider then, I mean, of course, if we go to this degenerate point where T0 equals T1, yes, of course, then it's 0, but we're looking for the maximum. Yeah, so what would help is to actually to have the return somewhere close to this point here. Yeah, because this is where the maximum of the vector potential is. And we already have 2 UP. So this is the obvious minimum for the maximum. E squared over 2m A naught minus 0. This would be the 2 UP. Sorry, and so this would be the E1 is certainly larger than that. And it's certainly smaller than the following. Yeah, so if we could completely freely choose emission time and recollision time, then we would want it to be, and in order to make it a maximum, we would want it to be emitted here and recollide there. Yeah, because then because the vector potential then goes from the positive peak to the negative peak, and or vice versa. So this would be A naught minus A naught, and that would be 2 times A naught. And if you recall, A naught equals 4 UP, then this would be 8 UP. Yeah, so the recollision time is certainly between these values. And yeah, as we discussed, it would be favorable to have the recollision somewhere close to this point. Yeah, so why did we divide by half? Because the energy is a half m over 2 times v squared.
Yeah, the first term
This one?
there is no.
Oh yes, I forgot that one. Thank you. Okay, so obviously it would be nice to recollide somewhere close to here. Yeah, so this would be a good candidate for this maximum energy. Do you agree? This would give us here. This would give us the maximum vector potential, and here we're actually beyond the minimum. So this would surely be more than 2 UP. So first candidate. Omega T1 is 3 pi over 2, yes. Yes, so here a little bit beyond omega t equals 0. And here it's 3 pi over 2 or so. And then you you can find this time here. Is, for example, using a ruler here with this with the graphical method, and what you will find is that Yes, this is for, yes, that's correct. That's correct. Yeah, so we can, so, I mean, you apply the graphical method to f, but then you have to calculate the values for a. Yeah, but I mean, I could draw a here if you want. So a would have a maximum here, and then it would have a minimum there, and another maximum here. So a would be something like this, right? No, yeah, and here it's not a very good sign that I drew there, right? Yeah, so here it would already be 0. This would be the next 0 crossing. Yeah, so you have to plug it in for a. But this plot becomes a little busy. But the idea is, yeah, if you want to be here at the maximum, which is the minimum for f of t, then the emission time would be somewhere here, and you could then read off the value of a from this. And if you do this, so this is t naught would be that, and then we plug these values into that equation. Yeah, so plug this in here and this in there, and then we obtain E1 equals 2.8 UP. And you will receive a homework task in the next one where you actually where you do this numerically, and what you will find is the following value that I will tell you now, and you should never forget again. Numerical solution. So you do it as we discussed above, right? You consider all the emission times, and then you propagate until the location changes its sign, and then you just evaluate the energy. And what you will find is the maximum value is 3.17 UP. Yeah, 3.17. And I give you also the times for emission and times for recollision. Yeah, so T naught is 0.05 times the optical cycle, and T1 is 0.70 times the optical cycle. Yeah, so the electron spends approximately 2/3 of an optical cycle in the continuum, and by that it gains the maximum energy. And you will learn next week that this is a very important number that you encounter over and over again in the field. Okay, thank you very much for the attention. Are there questions before we close?
I have a question.
Yes, please.
About the
About the homework, okay. Yeah, so maybe I close this first and we